Hello everyone. In this session, we are going to see some topics in iterative improvement and approximation algorithm. First topic is iterative improvement. It is a powerful algorithm design used for solving optimization problems. This technique processes by starting with an initial feasible solution and then repeatedly improving this solution through a series of small changes until a near optimal solution is found. Some of the methods in iterative improvement are maximum flow problem, maximum matching in bipartite graph, and stable marriage problem. Let's see one by one. First method is maximum flow problem. We start with a zero flow, that is zero amount sent through each edge are separated from the edge capacities by the slashes. So the maximum flow problem is to find a flow of largest value for a given network. This maximum flow problem is also called as augmenting path method and also known as Ford-Fulkerson method. As I said before, it starts with a zero flow. Then on each iteration, it tries to find a path from source to sink along which some additional flow can be sent. Such path is called flow augmenting. If a flow augmenting path is found, we adjust the flow along the edges of this path to get the flow of an increased value and try to find an augmenting path for the new flow. If no flow augmenting path is found, then we can say that the current flow is optimal. Let's see an example of maximum flow problem. So there are three figures here. In the first figure A, it shows the initial configuration of the flow network. Each edge is labeled with 0 slash capacity indicating 0 initial flow. For example, the edge from node 1 to node 2 has capacity 2, shown as 0 slash 2, and from node 2 to 3 has capacity 5. It is represented as 0 slash 5. At this stage, no flow has been sent from the source to the sink. Next, in figure B, it is said about the graph reflects the network after applying the first augmenting path. The path 1 to 2, 3 to 5, 5 to 6 has been chosen, pushing 2 units of flow, which is the minimum residual capacity along the path. In figure B, the graph reflects the network after applying the first augmenting path. The path from 1 to 2, 2 to 3, 3 to 5, 5 to 6 has been chosen, pushing 2 units of flow, which is the minimum residual capacity along the path. Edge labels now reflect this flow update as 2 slash 2, 2 slash 5 and so on. At this stage, a partial flow is distributed along one complete path from source to sink. In figure C, it deals with an intermediate residual graph after the first augmentation. It shows used capacities and residual capacities along all edges. Additional paths are considered for pushing more flow, such as 1 to 4, 4 to 3, 3 to 5, 5 to 6, with possible backtracking and adjustments using reverse edges. So for example, edge 1 to 4 as flow 1 slash 3 and edge 4 to 3 as 1 slash 1, indicating 1 unit of flow is pushed through this new path. Through successive iteration and updating the flows, The algorithm continues until no more augmenting path with residual capacity exists. Next topic is the maximum matching in bipartite graph. The matching in a graph is a subset of its edges with the property which has no two edges share a vertex. The maximum matching problem is a problem of finding maximum matching in a given graph. So let's see an example for this maximum matching. The bipartite graph is divided into two disjoint sets, set V and set U. So V indicates 1, 2, 3, 4, 5. And set U indicates 6, 7, 8, 9, 10. Each edge represents a possible pairing between an element in V and U. The goal is to find the maximum number of matching such that no two matchings share a vertex. That is, each vertex is used only once in a pair. I will explain you this example with step-by-step process. So figure A, we begin with all vertices unmatched. Our first goal is to find an augmenting path, which is a path that alternates between unmatched and matched edges, starting and ending with unmatched vertices. So the first augmenting path will be 1 to 6. We find a direct edge from vertex 1 to 6. So both are unmatched. We match them. The edge 1, 6 becomes part of current matching. So that is drawn as thick line. In the figure B, it shows the augmenting path from 2 to 6, 6 to 1, 1 to 7. Here we find an alternating path that begins at 2, which is unmatched, and hence at 7, that is also unmatched, with intermediate matched or unmatched edges. So here we can see that 2 to 6 is unmatched. If we match 6 to 1 is matched, 1 to 7 is unmatched. So we flip the matching status along this path and remove 1, 6 and we add 2, 6 and 1, 7. This increases the total matching by 1, forming a better configuration. In figure C, the augmenting path from 3 to 8, 8 to 4, 4 to 9, 9 to 5 and 5 to 10. So after flipping, the new matched edges are 3, 8, 4, 9 and 5, 10. So the final outcome will be the matching pairs are 1, 7, 2, 6, 3, 8, 4, 9 and 5, 10. So total number of matches are 5, which is the maximum possible for this graph, as each vertex in V is matched exactly once. The next method of iterative improvement is the stable marriage problem. The stable marriage problem is a classic problem that deals with finding a stable matching between two equally sized sets of entities given their preferences for each other. Consider a set Y equal to M1, M2 up to Mn of n men, and a set X equal to W1, W2 up to Wn of n women. So each man has a preference list ordering the women as potential marriage partners with no ties allowed. Similarly, each woman has a preference list of the men also with no ties. the same information will be presented by the n cross n ranking matrix. So the image shows the execution of the stable marriage algorithm through a series of steps helping to match 3 men, Bob, Jim and Tom, with 3 women, Anne, Lee and Sue, based on their preference list. The goal of the algorithm is to find a stable matching where no 2 individuals would prefer each other over their current partners. So let's see how an algorithm works step by step in the following diagram. Now let's see how an algorithm works step by step for the below example. Now let's see how an algorithm works for the following example. Each man proposes to woman in order of his preferences, and each woman can accept or reject the proposal based on her own preference list. Here, the accepted proposal is shown in boxed cell. The rejected is shown in underlined cell. Each row shows the rankings of women for each man. So, first step. Here, Bob proposes to his first choice, Lee. So, Lee accepts since she is free. So, draw a box around Lee for Bob accepted. In the second step, Jim proposes to Lee. That is his first choice. But Lee prefers Bob over Jim. That is, Bob ranks higher in her list, so she rejects Jim. Here, put underline around Lee for Jim. That is, he rejected. In the step 3, Jim, after rejection, proposes to his second choice, that is Sue. Sue accepts as she is free. So, put a box around Sue for Jim. In the step 4, Tom proposes to Sue, which is his first choice. But Sue prefers Jim over Tom, so she rejects Tom. So here you put underline around Sue for Tom. In the step 5, Tom proposes to his second choice, Lee. So Lee prefers Tom over Bob. So she accepts Tom and rejects Bob. So draw a box for Tom to Lee and put underline for Bob to Lee. In the step 6, now Bob is free again. He proposes to his next choice, Anne. Anne accepts as she is free. So put a box for Bob to Anne. So the final matching will be Bob is matched with Anne, Jim is matched with Sue, and Tom is matched with Lee. So this outcome is stable. That is, no 2 people prefer each other over their current partners. There are no blocking pairs, so the solution is valid and optimal. So that's all about iterative improvement. Next, we move on to approximation algorithm. So approximation algorithm refers to the efficient algorithm that finds a solution to one optimization problems that is close to optimal solution. These problems are expensive to solve exactly, especially for large inputs. So when this approximation algorithm is used, when finding an optimal solution is very difficult. In some cases, the exact solution is not needed, and near optimal solution can be found fast. The idea of optimization algorithm is to develop polynomial time algorithms to get the near optimal solution. Next, the optimization problem. So it deals with the problem of finding best option among all feasible solutions. The various important problems involve in finding the best possible way to accomplish the task, which is often done by finding the maximum or minimum values to a function. So the maximization problem is finding the maximum optimal value, and the minimization problem is finding the minimal optimal value. The example of optimization algorithm are traveling salesman problem and knapsack problem. Under traveling salesman problem, we have three methods: nearest neighbor algorithm, multi-fragment heuristic algorithm, and twice around the tree algorithm. Let's see the methods one by one. The first method of traveling salesman problem is nearest neighbor algorithm. In this method, the nearest neighbor algorithm starts at a chosen vertex and repeatedly visits the nearest unvisited vertex until all vertices are visited, then returns to the start. So let's begin from vertex A. Start at A and nearest to A is B, so the distance is 1, so go to B. From B, the nearest unvisited vertex is C, so the distance for C is 2. So next we are going to C. So from C, only unvisited vertex is D. The distance is 1, so visiting to D. Then again from D, it is returning to A. The distance is 6. So now the path is A to B, B to C, C to D, D to A. So the total cost will be 10. The nearest neighbor is simple but may not give the best approximation, especially with high return cost. Next method is multi-fragment heuristic. The multi-fragment heuristic works by sorting all edges in increasing weight, adding the shortest edges one by one to the tour, that is avoiding the cycles until all vertices are connected in a single tour. Each vertex must be included in exactly 2 edges. Here the sorted edges are A to B, that is 1, C to D is 1, B to C is 2, A to C is 3, B to D is 3, and A to D is 6. Now select edges while maintaining the degree less than 2 and avoiding the cycles. Add A to B, next add C to D and add B to C. Now A to B to C is connected and add A to D to complete the cycle. Now the path will be A to B, B to C, C to D and D to A. The total cost is 10. So here multi-fragment heuristic often gives a better or equal solution when compared to the nearest neighbor. The last method is twice around the tree algorithm. Here we follow the steps like: first step, we should build a minimum spanning tree of a graph according to the given instance of the traveling salesman problem. The next one, we should start with an arbitrary vertex, walk around the minimum spanning tree and record all the vertices that we pass. The third step, we should scan the vertex list obtained in step 2 and eliminate all the repeated occurrences of the same vertex except the starting one. We then form a Hamiltonian circuit of all vertices that are remaining on the list, which is the output of the algorithm. So by using this, 3 steps, we need to build outcome for the given image. So here we are applying this algorithm to the graph and getting the minimum spanning tree of this graph with edges a comma b, b comma c, b comma d and d comma e. Next step is twice around the tree walk that starts and ends at A is A to B, B to C, C to B, B to D, D to E, D to B, B to A. So here we are eliminating the repeated edges. So we are eliminating the second B, second D and third B, and so that here it forms an Hamiltonian circuit after removing the repeated ones. So the length of this tour is 37. So this tour is not an optimal solution, it is a better solution. So next topic is knapsack problem. The given image tells the step-by-step application of approximation scheme with k equal to 2 parameter. This method seeks to find a near optimal solution efficiently when an exact solution is expensive. The left part of the image displays the knapsack instance with 4 items, each categorized by a weight, value and their value to weight ratio. So the maximum capacity of knapsack bag is 10. So for an example, the empty set results in addition of items 1, 3 and item 4, producing a total value of 69. Similarly, when the subset 1 leads to the same total when item 3 and 4 are added. Some subsets like 1, 2 are labeled not feasible due to their combined weight exceeding the capacity. The boxed entries represents the total value achieved by these different combinations. Similarly, the best combination found is total value will be 69. So the algorithm gives 1, 3, 4, which is the optimal solution for this example. Thank you for watching the video.